Hi, we're going to end the course with a series of 4 units looking at the prospects for artificial general intelligence from various perspectives. And I'm going to start by discussing various classical theorems about universality. We're all familiar with Turing universality for programming languages, the idea that any computational substrate that's sufficiently expressive can do any computation that any other computational substrate can do. And this Turing universality underlies most people's faith that artificial intelligence, general artificial intelligence, is possible. Most people believe that it's a question of when, not a question of whether. So let's start by looking at some classical universality theorems. So the Kolmogorov-Arnold representation theorem from 1956. And this theorem is about, makes a claim about all continuous functions of n inputs. So if you consider a function, continuous function of n inputs, where each input is in the interval 0, 1. So it's taking n inputs in the interval 0, 1. And the first thing I want to do is think about how expressive these functions are. So I think of this is the interior of a Boolean n cube. I've just drawn it here. And a continuous function can assign an independent value to every corner of that cube. And I can think of the corners of the cube as bit strings. Every coordinate is either 0 or 1 at a corner. So this function can assign 2 to the n different values, independent values to these corners. And then you can always interpolate and fill the interior. So these functions really do have at least, I mean, they have many more, but at least 2 to the n different independent values. So we have a representation theorem that's saying that for any such function that has an enormous amount of information, we can express that function with a polynomially sized 2-layer circuit of a certain kind. So what kind? So for any such function, there exists activation functions from R to R and continuous functions, which I'm writing as Wij from R to R. All of these functions are just reals to reals. They're not taking more than one input. All of these are reals to reals, such that if I build this circuit, I can exactly reproduce the function. So what's the circuit doing? Well, inside this sum, you're taking each input to this function. This is one of the inputs to the function, and you're passing it to this function. So this is an R to R function, and I'm summing that over all the inputs. So these are continuous R to R functions. Each one is looking at one of the inputs, and I'm summing that over all the inputs, and then I'm passing that sum through another R to R function. And then I have 2n plus 1 copies of this whole thing that are with different functions at each copy. And if I add together 2n plus 1 of those functions, I can exactly reproduce the function of n arguments. So this is looking like a 2-layer network can simulate any function of n arguments. So this is kind of shocking. I think it's kind of shocking. But what I'm going to do is show a related theorem that gives you some intuition as to how this can be true and why it might not be as shocking as it looks. So if I drop the condition that these functions are continuous, right? This theorem says that this can be done when these functions are continuous. If I drop the requirement that these functions are continuous, then a much simpler representation with a much simpler proof is possible. So now what I'm going to do is I'm going to take each input. It's got n inputs. I'm going to take each one of the input and pass it through a function from R to R. And what this function from R to R is going to do is it's going to take the digits of this. So I can think of this in binary, say, as 0.011000, a bunch of digits. And I'm going to have this function just spread those digits out such that each digit occurs every nth position. And then the different functions on the different inputs are going to all going to spread them out, and they're going to put them at different phases. And now when I add all those together, each position in the number is only getting input from one of the inputs. And when I spread them out and add them together, I can preserve all the digits of all the inputs. And then I can pass that through another function that pulls those digits out and exactly reproduces this function. And applies this function to a reconstruction of the n inputs that I get from reconstructing the inputs. This is preserving all of the information in all of the inputs. Okay, so this theorem, the Kolmogorov-Arnold theorem, relies on something I'll call real number abuse. It's relying heavily on the fact that actual real numbers have infinite precision. And this continuity condition is not very strong. Continuity is a weak condition. There exist everywhere continuous but nowhere differentiable functions. So if you try to actually use this theorem in practice, these functions get wildly non-smooth. They're continuous, but they're not like Lipschitz. They can not be differentiable. I'm always suspicious of something that's relying heavily on the fact that real numbers have infinite precision. I like to think of real numbers and finite precision floating point numbers as being similar. You should always be able to replace your real numbers by finite precision floating points. Okay, here's another representation theorem, Cybenko's universal approximation theorem. So this theorem is more closely related to actual neural networks. But again, it's about an arbitrary continuous function of n inputs on the unit interval. And what it's going to say is that for any function, any such function, that function can be arbitrarily well approximated by a two-layer neural network. So now we're just talking about linear threshold functions and adding together the outputs of linear threshold functions. So, so this function can be written as a two-layer neural network. This is just a standard linear threshold unit. It can be represented as a weighted sum of linear threshold units, such that no matter what accuracy required, there exists a two-layer network such that that two-layer network is within epsilon of the function. So any such function can be represented arbitrarily well with a two-layer neural network. Okay, so this is also turns out to not be a very surprising theorem. It's a general theorem about measurable functions, that any measurable function can be represented arbitrarily accurately by a function that's piecewise constant, where the pieces are even little squares or boxes in your space. So what's going to happen is the number of pieces is going to be huge, but then I can build a linear threshold unit for each piece that just activates when the input is right at that piece. So what I'm going to do is think about the Boolean case, because the Boolean case, I always think it's useful to think about the Boolean case as a special case of the analog case of deep neural networks. So if we have a Boolean case, and we just think of the 2 to the n possible Boolean inputs, the corners of this cube, I can always represent any function of a finite set of inputs by defining an indicator function for each input, and then adding together all the indicator functions where only one of these indicator functions is turned on for any given input. Okay, so now I can do the same thing with a two-layer neural network. I can write a linear threshold unit that only activates when the input is precisely aligned with this weight vector, right? And I can make that as accurate as I want, right? So I make this linear threshold unit activate when you're at a particular point or a particular input. So that's analogous to saying I've got an indicator function for particular positions. And then if I add all those indicator functions together, I can reproduce the function arbitrarily accurately. In the case of Boolean functions, I could reproduce it essentially exactly. But the point is, the number of these linear threshold units is going to be exponential, right? You're thinking of the function as a big table of input-output pairs, and you're creating a linear threshold unit for each input-output pair individually. So thinking of functions as enormous lists of input-output pairs is not a useful way to think, right? These lists are exponential or super exponentially large. Okay, representing functions by circuits. Deep circuits can represent functions more compactly than shallow circuits. So we saw in the case of a two-layer neural network, the network's going to be exponentially wide, exponentially many linear threshold units. If we go to deeper circuits, we can represent things compactly narrowly with a finite sized circuit, when we include its width, that we can't represent with a two-layer neural network. And theorems of this form have been proved in circuit complexity theory. So in 1987, there's a theorem that says that if I bound the depth, if I have a fixed depth and I want to compute parity, so I've got a number of inputs, I want to know if the number of ones in the input is even or odd. That's parity. If I want to know, it's the number of ones in the input, even or odd, if I bound the depth, then as n goes to infinity, that circuit has to be exponentially wide, has to get exponentially wide. So bounded depth circuits require exponential width to compute parity. But of course, you can compute parity if you let the depth of the circuit increase, be linearly deep in the size of in the number of inputs. So that's saying that the deep circuits are smaller in terms of the number of gates. Mattis Telgarsky, who's now at the University of Illinois, Urbana-Champaign, proved a theorem in 2016 showing, establishing incremental expressive power when I make the circuit just one layer deeper. And so if you make a circuit one layer deeper, there are functions that you can express one layer deeper with polynomial width that you cannot express one layer shallower, or if you express them one layer shallower, they get exponential width. But the limits, complexity theory is hard, right? We all believe P is not equal to NP, but nobody can prove it. So if you look at the provable statements of circuit complexity theory, they tend to be very weak, and they don't provide any guidance into how to design neural architectures. So we know and we accept that deep networks can compute things that shallow networks can't. But that's sort of all we're learning from these theorems. Okay, finally, representing functions by programs. Now we're talking, right? C programs or Python programs are clearly very expressive, and they let us write things quite compactly. And furthermore, we have these nice generalization guarantees that hold over the space of all Python programs or C programs. So if I let F be a Python program, and I talk about the number of bits it takes to write down F, and this is most interesting when I pass F through a compression algorithm. So I take the number of compressed bits that it takes to represent my Python program. I get this generalization guarantee that says that the generalization performance of my Python program is going to be near its training performance, provided that its bit length is short enough. Simple programs will generalize. And this holds the whole class of all Python programs. That's very nice, but the problem is that we don't know how to search over the space of Python programs to find the program with low training error. So there's a huge search. We don't know how to do gradient descent or effective gradient descent on the space of all programs. And I'm going to come back to this in later units. So we've got 3 more units on ways to think about approaching AGI, and we'll move on to the next unit.